Let me start somewhere you probably already feel is obvious. And that is exactly why it is dangerous. You look up at the night sky. Or maybe you don't even bother to look anymore because the conclusion seems so straightforward that it barely needs thinking. With that many stars, with that many planets, how could we possibly be alone? It sounds reasonable, almost embarrassingly reasonable. Like saying if you scatter billions of seeds across a continent, at least some of them are going to grow. And the universe is not scattering seeds across a continent. It is scattering them across something so vast that even our best metaphors start to break down before they reach the scale of what is actually out there. Think about just our galaxy for a moment. Not the whole universe, just the Milky Way. Because even that single system is already absurd. Roughly 200 billion stars, give or take. And that number is not a poetic exaggeration. It is an estimate grounded in observation, in measurements of stellar density and galactic structure around most of those stars. As far as we can tell, planets are not rare accidents, but common outcomes of how star systems form. Disks of gas and dust collapsing into worlds of every size and composition you can imagine. Some are gas giants, some are frozen wastelands, but a fraction of them, not zero, not vanishingly small, sit at distances where temperatures allow liquid water to exist on the surface. And that detail matters because, at least as far as we know, water is not just convenient for life, it is practically synonymous with it. Now here is where your intuition starts to get you into trouble, because your brain is not built to handle multiplication at this scale in any meaningful way. You take 200 billion stars, you multiply by the fraction that have planets, then by the fraction of those that are in habitable zones, then by the fraction that might develop life. And even if you choose extremely conservative numbers at every step, the result is still enormous. Not large in the way a city is large, not large in the way a country is large, but large in the way that makes your sense of uniqueness feel almost arrogant. It is like standing on a beach that stretches beyond the horizon in every direction, picking up one grain of sand that happens to be blue, and declaring that no other blue grain could possibly exist anywhere else. That is not a scientific conclusion. That is a psychological comfort. And the Milky Way is just one galaxy. When you widen the frame, the situation becomes almost absurd in a different way, because now you are dealing with not billions, but trillions. At least 2 trillion galaxies in the observable universe, each one with its own hundreds of billions of stars, its own planetary system, its own opportunities for chemistry to stumble into biology, and for biology, given enough time, to stumble into intelligence. You start stacking these numbers together, and something interesting happens. Something that feels less like speculation and more like inevitability. It begins to feel as though life is not a rare miracle, but a common consequence. As though intelligence is not a singular accident, but a recurring pattern written into the fabric of matter itself. And then time enters the picture, and time makes everything even more lopsided. Our sun is about 4.5 billion years old, which sounds ancient when you compare it to human history. But on a cosmic scale, it is not particularly early, not particularly late, just somewhere in the middle. There are stars in this galaxy that formed billions of years before our sun existed, which means there are planetary systems out there that had a head start, not of thousands of years, not of millions, but of billions. Try to sit with that for a second. Not just as a number, but as a difference in development. We went from primitive tools to radio telescopes in roughly 10,000 years, a blink of an eye in geological terms. give a civilization an extra billion years, let alone 5. And whatever they become is not just more advanced than us. It is so far beyond our current understanding that even our best guesses start to feel naive. So the argument builds itself in your mind, almost without effort. If life arises in even a tiny fraction of suitable environments, then the universe should be full of it. If intelligence emerges from life even occasionally, then thinking beings should be scattered across the stars. And if even a small percentage of those beings survive long enough to develop technology, to build machines, to harness energy on scales we are only beginning to imagine, then surely some of them would have found a way to cross the distances between stars. After all, look at us. In just over a century, we went from powered flight to stepping onto another world. From fragile wooden planes to machines that leave the planet entirely. Extend that curve. Stretch it over millions of years instead of decades. And it becomes very hard to believe that interstellar travel remains out of reach. At this point, the conclusion feels almost forced, as if logic itself is pushing you toward it. They should exist. They should be older. They should be more capable. And given enough time, they should have spread, explored, visited, not everywhere, perhaps, but somewhere, sometime. And if all of that is true, then the quiet sky above you starts to feel less like an empty space and more like a question that has not been answered yet. You might be tempted at this point to lean back and say, all right, this Feynman, they exist somewhere out there. So what's the real obstacle? And this is where everything quietly collapses. Not with some dramatic explosion, but with a slow, uncomfortable realization that the word far has been lying to you your entire life. Because when you say something is far on earth, you mean hours, maybe days, at most weeks, even crossing an ocean, which once felt like an impossible journey, is now a routine inconvenience. But space does not play by those rules. And the distance to the nearest star is not just farther than what you are used to. It belongs to a completely different category of distance altogether. Take the closest star system to us, Proxima Centauri, often introduced as if it were just the next stop down the road. A neighbor in cosmic terms, it sits about 24 light years away. And that number sounds manageable until you remember what a light year actually means. It is not a unit of time. It is a unit of distance. The distance that light itself travels in 1 year, moving at roughly 300 kilometers per second. The fastest speed anything in the universe is allowed to have. So when you say 24 light years, what you are really saying is that even light, which crosses the entire Earth in a fraction of a second, needs over 4 years to make that journey. The light leaving Proxima Centauri today will not reach your eyes until you have aged, changed, and moved on with your life. Now let me make this hurt in a more tangible way, because raw numbers do not register properly in the human brain. The distance to Proxima Centauri is about 40 trillion kilometers, a number so large that writing it down does not help you feel it. So instead, imagine shrinking the entire solar system to something you can hold in your head. Picture the sun as a grapefruit sitting on a table. Earth becomes a grain of sand orbiting about 10 meters away. Jupiter, a small marble further out. Neptune somewhere near the edge of your neighborhood. That already stretches your intuition a little. But now ask yourself where the nearest star would be in that same scale. Not in the next room, not down the street, but another grapefruit placed thousands of kilometers away, effectively on the other side of a continent. Everything we have ever built, every probe, every spacecraft, has only managed to crawl around within the tiny bubble surrounding that first grapefruit. And you might say, well, of course our current technology is slow. It is primitive. Give it time. That sounds reasonable. But even before we talk about faster ships or better engines, look at what our fastest machines are actually doing right now. The Voyager probes, launched in the 1970s, are among the fastest objects humanity has ever built, moving at roughly 17 kilometers per second. That is fast enough to leave the solar system, fast enough to feel like real progress on a human scale. Yet at that speed, reaching Proxima Centauri would take on the order of 70,000 years. 70,000. Long enough that everything you call history, from the earliest cave paintings to modern civilization, fits comfortably inside the travel time of a single journey to the nearest star. And it gets worse in a way that is almost unfair, because Proxima Centauri is not a typical distance. It is an unusually short one. It is the closest possible case, the best case scenario nature offers us. Most stars in the Milky Way are not 4 light years apart, but tens, hundreds, even thousands of light years apart, depending on where you look. The galaxy itself spans about 100,000 light years from end to end, which means that even if you could somehow hop from one nearby star to the next, you are still dealing with a structure so vast that crossing it becomes a project measured not in lifetimes or civilizations, but in epochs. And this is the part where your intuition tries one last escape route, because it whispers that distance, no matter how large, is still just distance. We have always found ways to go farther, to move faster, to shrink the world through better technology. Oceans used to be barriers until we built ships, mountains until we built roads, the sky itself until we built aircraft. So it feels natural to assume that interstellar space is just the next version of the same problem, waiting for a more advanced solution. But that assumption carries something hidden inside it, something you have not questioned yet, which is the idea that distance is the only thing standing in your way. Because once you really look at these numbers, not just glance at them, but sit with them long enough for them to feel uncomfortable, a different kind of question starts to form. Not how far is it, but what would it actually take to cross that gap? And that question does not lead where your intuition expects it to go. At some point, almost inevitably, your mind reaches for the simplest escape: go faster. If the distance is unbearable, then reduce the time. If 70,000 years is absurd, then build something that can cross it in decades or years, or at least within a single lifetime. That instinct feels so natural that it barely seems like an assumption at all. Because on Earth, speed has always been the lever that solves distance. Horses gave way to trains, trains to airplanes, airplanes to rockets, and every step along that progression reinforced a quiet belief that there is no true limit, only temporary ceilings waiting to be broken. But the universe does not share that belief. And this is where Einstein enters the story, not as a historical figure, but as the person who discovered that speed itself is not just difficult to increase, it is fundamentally bounded in a way that no amount of engineering can negotiate with. The speed of light, about 300,000 kilometers per second, is often introduced as a very large number, and that is already misleading. because it encourages you to think of it as a challenge, something to approach and eventually surpass with better technology. In reality, it is not simply the speed at which light happens to travel, it is woven into the structure of space-time itself, acting as a conversion factor between space and time. A constant that shows up in the deepest equations describing how the universe behaves. When physicists write down the laws of motion at high velocities, they do not find a barrier you crash into, but something stranger and more restrictive, an asymptote you can approach forever without ever reaching. The closer you get to the speed of light, the harder it becomes to go any faster. Not linearly, but in a way that escalates without mercy. You can feel this most clearly when you look at how energy behaves. In everyday life, pushing something faster is straightforward. Double the force, roughly double the acceleration, and the object speeds up accordingly. That intuition works because at low speeds, the equations simplify, and the resistance to acceleration, what we call inertia, appears constant. But as velocity increases and begins to approach a significant fraction of the speed of light, that simple picture starts to break. The object does not literally gain mass in the naive sense, but it behaves as though it does, becoming increasingly resistant to further acceleration. Each additional increment of speed demands more energy than the last, and this demand grows dramatically as you push closer to the limit. Imagine trying to run across a surface that changes beneath your feet depending on how fast you move. At a slow pace, the ground is firm and predictable, but as you accelerate, it softens into sand, then thickens into mud, then turns into something like syrup that clings to your legs and resists every motion. No matter how hard you push, the resistance increases faster than your effort. And the faster you attempt to go, the more the environment pushes back. Space-time behaves in a disturbingly similar way. It does not forbid motion, but it punishes attempts to approach the ultimate speed limit with a kind of escalating resistance that no finite resource can overcome. And this is not a theoretical curiosity tucked away in obscure equations. It is one of the most thoroughly tested aspects of modern physics. Particle accelerators, atomic clocks, high-energy experiments. All of them confirm the same behavior. As particles are pushed to higher and higher speeds, the energy required to continue accelerating them rises steeply. And despite decades of technological advancement, no experiment has ever succeeded in pushing a massive object to the speed of light. The limit holds, not as a practical inconvenience, but as a rule built into the geometry of the universe. Now consider what this means for the idea of interstellar travel. Even if you design a spacecraft capable of reaching, say, 10% of the speed of light, which is already far beyond anything we can currently achieve, you have not solved the problem. You have only made it slightly less impossible. The trip to Proxima Centauri would still take over 40 years. And pushing beyond that speed quickly becomes a losing battle against the laws you are trying to exploit. Doubling your speed does not simply double your energy requirements. It multiplies them in a way that becomes increasingly unforgiving as you approach relativistic regimes. By the time you start thinking about speeds like 50 or 90% of light speed, the energy demands are no longer just large. They are approaching scales that begin to rival the total energy output of entire civilizations. And here is the subtle but crucial shift you have to make in your thinking. This is not a problem of insufficient cleverness, not a matter of waiting for a breakthrough that will suddenly make the impossible routine. The speed of light is not a wall that can be climbed with better tools. It is a feature of the landscape itself. You do not overcome it any more than you overcome the fact that time flows forward or that causes precede effects. It is part of the framework within which all physical processes occur. And every attempt to bypass it runs into the same conclusion. The closer you get, the more the universe demands from you, until the price diverges beyond anything you can pay. So when you return to that earlier instinct, the one that says, just go faster, you find that it rests on an assumption that no longer holds. Speed is not a free parameter you can dial up indefinitely. And distance is not something you can shrink arbitrarily by throwing enough ingenuity at the problem. The limit is real. It is absolute, and it forces you to confront a different question. One that is far less comfortable than the first. Not how fast you want to go, but how much you are willing or even able to pay for every additional fraction of that speed. Let's say you are still not convinced, and honestly, you shouldn't be, because up to now, everything we have talked about feels like a set of limits, but not yet a final answer. You might still be thinking, fine, we can't reach the speed of light, but we don't need to. We just need to get close enough. That sounds reasonable. And now the problem becomes much more uncomfortable, because we are no longer talking about what is allowed. We are talking about what it actually costs. So let's make this painfully concrete. Imagine a spacecraft with a mass of about 100,000 kilograms. That is roughly the size of a large airplane. Not something absurd, not some science fiction megastructure, just a serious piece of engineering. Now ask a very simple question. What does it take to push that object to just 10% of the speed of light? The answer is not a clever trick. It is energy, an enormous amount of energy. To get that spacecraft up to 10% of light speed, you would need an amount of energy that is comparable to a noticeable fraction of everything humanity produces in an entire year. Not one country, not one industry, but all of it combined. Every power plant, every nuclear reactor, every solar panel, every wind turbine, all working together for a full year. And a single spacecraft takes a meaningful slice of that just to get moving. And remember, this is only 10% of the speed of light. At that speed, the trip to the nearest star still takes more than 40 years. Now here is where things start to turn against you in a way that feels almost unfair. That energy does not sit conveniently in a tank waiting to be used. You have to generate it, store it, and convert it into motion. No system is perfect. No engine is 100% efficient, even if you imagine something unbelievably advanced, something that wastes almost nothing. You still lose some energy along the way. And every bit you lose means you have to generate even more. But all of that is still not the real problem. The real problem is how rockets actually work in space. You cannot push against anything. There is no ground, no air, nothing to brace yourself against. The only way to move forward is to throw something backward. You carry fuel, you burn it, and you eject it out the back. The reaction pushes you forward. That is it. There is no alternative. And here is the trap that closes the moment you try to go fast. That fuel has mass. So before you even start your journey, you are not just accelerating your spacecraft. You are accelerating all of the fuel you are carrying. And that fuel needs more fuel to push it. And that extra fuel needs even more fuel. It stacks on top of itself in a way that does not grow slowly, but explodes. You want a little more speed. You do not need a little more fuel. You need a lot more fuel. Then that fuel makes your ship heavier. which means you need even more fuel to push the extra weight. And that added fuel also has weight. It compounds. It feeds on itself. This is what physicists call the rocket equation. And the name sounds harmless, but it behaves like a kind of tyranny. It does not negotiate with you. It does not care how advanced your civilization is. It simply tells you that the faster you want to go, the more your spacecraft turns into fuel with chemical rockets, the kind we use today. The situation becomes ridiculous almost immediately. Trying to reach even a tiny fraction of the speed of light would require so much fuel that the actual spacecraft becomes almost irrelevant. A small payload buried under an absurd mountain of propellant. So you move to better ideas. Nuclear propulsion, fusion, maybe even matter and antimatter, where mass can be converted into energy with incredible efficiency. That helps, but it does not save you. The equation still applies. You are still throwing mass out the back, and the exponential growth is still there, even with a hypothetical perfect engine, something that wastes nothing and converts fuel into motion with absolute efficiency. The numbers are still staggering for long interstellar journeys at high speed. You could end up needing hundreds of thousands of kilograms of fuel for every single kilogram of spacecraft that actually arrives at the destination. The ship becomes almost entirely fuel, with a tiny fraction left for anything useful. And then, just when you think you have reached the destination in your calculations, something quietly doubles the cost. You have to slow down. If you do not slow down, you do not arrive. You just fly past your target at an enormous speed and disappear into space forever. Slowing down requires the same amount of energy as speeding up. The same fuel, the same problem, all over again. So everything you just paid, you pay again. At this point, the structure of the problem becomes clear in a way that is hard to ignore. Energy demands force you to carry fuel. Fuel increases your mass. Increased mass raises your energy requirements. And the entire system loops back on itself, each part making the others worse. This is not a single obstacle that you solve with a breakthrough. It is a chain of constraints that tighten together the harder you push. And what makes it unsettling is not just how large the numbers are, but how consistent the pattern is. Because every attempt to go faster, to go further, to make the journey practical, feeds directly into the same problem you were trying to escape by now. If you are still holding on to a way out, it probably looks something like this. Fine. Rockets are inefficient. Fuel is a nightmare. Energy is overwhelming. But what if we are thinking about this the wrong way entirely? What if truly advanced civilizations do not push themselves through space at all, but instead reshape space itself? Wormholes, warp drives, shortcuts through space-time. Ideas that sound less like engineering and more like bending reality to your will. And on paper, in the language of equations, some of these ideas are not pure fantasy. They appear as legitimate solutions to Einstein's field equations, which is exactly why they are so seductive, because they give you the feeling that physics itself might contain an escape hatch, if only you are clever enough to find it. Take wormholes, for example, often imagined as tunnels connecting two distant points in space so that you can step in one side and emerge on the other without crossing the distance in between. Mathematically, such structures can exist within general relativity, but the moment you ask what it takes to keep one open, the story changes. The equations demand something called negative energy density, a form of matter that does not behave like anything we have ever observed in bulk. Quantum theory allows tiny, fleeting instances of negative energy, such as in the Casimir effect, where closely spaced metal plates create a minute imbalance in vacuum fluctuations. But scaling that up from something microscopic to something capable of holding open a tunnel between stars is not just an engineering challenge. It is a leap across a gap that may not be bridgeable at all. The energy requirements alone are often described in terms comparable to the mass energy of entire stars, compressed and controlled with precision. We cannot even begin to approach. Warp drives sound more promising at first glance because they do not require the spacecraft itself to exceed the speed of light. Instead, the idea is to contract space in front of the ship and expand it behind, effectively moving the ship by moving space-time around it. The Alcubierre metric shows that such a configuration is mathematically consistent with general relativity. But once again, the details refuse to cooperate. The original formulation requires enormous amounts of exotic matter with negative energy, and even later refinements, which reduce the scale of the requirement, still depend on materials and conditions that may not exist in the real universe. And then deeper issues appear. Some analyses suggest that a warp bubble cannot be controlled from within, meaning you could not start it, steer it, or stop it using the ship inside. It becomes less like a vehicle and more like a phenomenon that you somehow have to already be inside before it exists, which is not a solution so much as a rearrangement of the problem. So the grand escape routes, the ones that seem to promise a way around the speed of light, begin to look less like hidden doors and more like mathematical curiosities. Possibilities that exist in equations but refuse to manifest in reality. And while you are still considering them, something else, much less glamorous, has been waiting quietly in the background. A problem so unassuming that it is easy to overlook. Space, despite what you have been told, is not empty. It is extremely sparse. Yes, but not empty. And that distinction becomes lethal the moment you start moving at relativistic speeds. At everyday velocities, a single atom drifting through space is irrelevant, something you would never notice. But speed transforms everything. Imagine driving through rain. At low speeds, the droplets barely register. Increase your speed, and they begin to sting. Increase it further, and each drop carries enough energy to dent surfaces. Now replace those raindrops with individual hydrogen atoms, and increase your velocity to a significant fraction of the speed of light. From the perspective of your spacecraft, those atoms are no longer gentle particles. They are incoming projectiles carrying energies comparable to high-energy radiation. They slam into your hull, into your electronics, into anything exposed, creating cascades of secondary particles that penetrate deeper into the structure. This is not a rare event. It is continuous. At high speeds, your ship would be bombarded by billions of these impacts every second across every square centimeter of its forward surface. Electronics would degrade, data would corrupt, biological tissue would suffer severe radiation damage. And shielding does not come for free. To protect against this relentless stream of high-energy particles, you would need thick layers of material, dense, heavy shielding that adds enormous mass to your spacecraft. And the moment you add mass, you're back in the grip of the energy and fuel problems we have already seen. Each solution feeding directly into the same constraints you were trying to escape. And then there is dust, which sounds harmless until you remember how energy scales with speed. Tiny grains, smaller than a human hair, drift through interstellar space. At low speeds, they are nothing. At relativistic speeds, each one becomes a microscopic bomb. When such a particle strikes your spacecraft, it does not bounce off. It vaporizes on impact, releasing a burst of energy that can punch into the hull, erode surfaces, and over long distances, gradually sandblast the front of the ship away. And unlike radiation, which can sometimes be mitigated with shielding, impacts are unpredictable. You cannot guarantee uniform damage. A slightly larger grain, encountered at the wrong moment, could cause catastrophic failure. So now you find yourself in a position that feels almost ironic. The grand, exotic ideas fail because they demand physics we do not know how to realize. And the mundane, unavoidable reality of space itself becomes dangerous in a way that scales with your ambition. The faster you try to go, the more hostile the environment becomes, until the very emptiness you hoped would make travel easier turns into a constant assault on your ship and everything inside it. And what makes this especially frustrating is how these problems refuse to stay separate. Because the shielding you need increases your mass. The mass increases your energy requirements. The energy requires more fuel. And the fuel compounds the entire system again. Nothing solves itself cleanly. Every improvement creates another burden. And the path forward does not simplify. It entangles. Let's imagine, just for a moment, that you are stubborn enough to push past everything we have said so far. You solve the energy problem. Somehow, you tame the rocket equation, or at least make it manageable. You build shielding strong enough to survive the interstellar medium. You accept the cost, the scale, the absurd engineering, and you still decide to go. Because after all of this, you might think the universe has not explicitly forbidden the journey. It has only made it unimaginably difficult. So perhaps, with enough determination, you can still cross the gap. And in a narrow, technical sense, you might be right. But this is where the problem changes in a way that is much harder to see at first. Because it is no longer about whether you can go, but about what it means to go, not in terms of distance or speed, but in terms of time, and more importantly, in terms of connection, because the moment you move at a significant fraction of the speed of light, time itself stops behaving the way you are used to, and what seemed like a journey through space quietly becomes something else entirely. Relativity does something deeply unintuitive. As your speed increases, time for you slows down relative to those who remain at rest. This is not an illusion, not a trick of perception, but a measurable, experimentally verified effect. Clocks moving at high speeds tick more slowly than stationary ones. Astronauts age very slightly less than people on Earth. At everyday speeds, the difference is negligible. But as you approach relativistic velocities, it becomes profound. Now this sounds, at first, like a gift. If time on your spacecraft runs slower, then from your perspective, the journey is shorter. You might travel to a star system dozens of light years away and experience only a handful of years on board. While decades pass on Earth, that feels like a solution, a way to make interstellar travel compatible with a human lifetime. But that interpretation hides something crucial, something that only becomes clear when you step back and ask what travel is supposed to accomplish. Because you are not traveling in isolation. You are leaving something behind. Imagine a journey to a star 50 light years away at a speed close to that of light. From your perspective, perhaps the trip takes 10 or 20 years. You age, you live. You experience the voyage as something finite, something contained within your own life. But back on Earth, 50 years pass before you even arrive. If you turn around and come back, another 50 years pass. More than a century has gone by in the place you once called home. Everyone you knew is gone. Not just older, not just changed, but gone. The people who launched you, the friends you spoke to before departure, the world you understood. All of it exists only in memory. Even if your ship returns perfectly, even if every system works exactly as intended, you are not returning to the same place. You are arriving in a future that has moved on without you, a future that may barely remember why you left. And the further you go, the more extreme this becomes. Travel to a star system hundreds or thousands of light years away, and the time difference grows from decades to centuries, from centuries to millennia. Civilizations rise and fall in that span. Languages shift. Culture transform. Technologies evolve beyond recognition. You do not come back as a traveler bringing knowledge from afar. You come back as a relic from another era, disconnected from the timeline that continued without you. So the idea of a visit begins to break down. A visit implies departure and return, interaction and exchange, a continuity between where you came from and where you are going. But relativistic travel destroys that continuity. It severs the timeline into two paths that cannot be reconciled in any meaningful way. You can leave, and you can arrive somewhere else. But you cannot maintain a relationship between the two ends of that journey in the way your intuition expects. And this is not just a human limitation, not just a problem of lifespan or memory. It applies to any civilization, no matter how advanced, because it is rooted in the structure of space-time itself. Even if you replace human travelers with machines, with artificial intelligence that does not age in the same way, the disconnect remains. Information cannot travel faster than light. Messages take years, decades, centuries to cross the same distances. By the time a signal reaches its destination and a reply returns, the context that gave that message meaning may no longer exist. So what looked like a problem of engineering reveals itself as a problem of meaning. Interstellar travel, even if achieved, does not function like exploration on Earth. It is not a matter of going somewhere, learning something, and bringing it back. It is closer to a one-way migration through time, a commitment to leave your origin behind in a way that cannot be undone. And when you look at it from that perspective, a different kind of question emerges. One that has nothing to do with physics equations or propulsion systems. Why would any civilization choose to do this at scale? Why invest enormous resources to send travelers who cannot meaningfully return, to establish connections that cannot be maintained, to create journeys that dissolve the very idea of home? Because once you see it clearly, the barrier is no longer just distance or speed or energy. It is the quiet realization that even if you could cross the stars, the act of doing so might erase the very thing you thought you were trying to preserve. By the time you reach this point, the question that once felt so simple has quietly changed shape. It is no longer, are they out there? Because everything we have walked through makes it very hard to believe that life and intelligence are rare in a universe this large. The real question, the one that keeps echoing underneath everything else, is the one Enrico Fermi famously asked in a much more casual setting. If all of this is true, if the numbers are so overwhelming, if civilizations have had billions of years to arise and develop, then where is everybody? At first glance, that question feels like a contradiction. The numbers push you toward abundance, while the silence suggests absence. And it is tempting to resolve that tension with imaginative explanations. Perhaps advanced civilizations choose to hide. Perhaps they observe from a distance, treating emerging worlds like ours as protected environments. Perhaps they evolve beyond physical form, or destroy themselves before reaching the stage where interstellar travel becomes possible. These ideas are interesting, and they say something about how we think, but they all introduce additional assumptions, layers of speculation stacked on top of a problem that may not require them, because there is a simpler way to look at it, one that does not rely on hidden motives or unknown behaviors, but on the same physics we have been following all along. If crossing interstellar distances is not just difficult, but fundamentally constrained by energy, by momentum, by radiation, and by time itself, then the absence of visitors is not mysterious. It is expected, not because no one exists, but because the universe does not make it easy or even practical for anyone to show up. And yet, something interesting remains. While moving matter across these distances runs into one barrier after another, sending information does not face the same kind of resistance. Electromagnetic signals, radio waves, light itself travel at the maximum speed allowed by the universe. They do not require you to carry mass. They do not demand exponential